Hello everyone, welcome to another video on differential calculus. I am still looking at rules of differentiation. We have looked at 4 rules of differentiation so far, and today we're supposed to be starting on the power rule, which says that if f of x equals x to the power n, then f prime of x is equal to nx power n minus 1. Now for us to prove this, we need two things. We need the factorial notation, and we also need the binomial theorem. So in this video, therefore, I'm going to look at the factorial notation, and then in the next video I'm going to look at the binomial theorem, and then finally end up with the proof for the power rule, and then move on to the other remaining rules of differentiation. All right, now for us to understand the factorial notation, which is basically n exclamation mark, we need to answer these questions here. I have put 3 questions here that we need to answer. Basically, the factorial notation is one of the concepts in what we call combinatorics, a branch of mathematics that deals with counting principles. So basically, we have the fundamental counting principle, we have the factorial notation, we have the permutation, and then we have the combination. Those 4 and other concepts together form what we call combinatorics, a branch of mathematics which is covered in part in high school, but it's covered in full in statistics at first year level in the university. So we're going to look at those aspects when I start looking at counting principles and probability to take care of grade 12 syllabus. But in this case, I just want to focus on what we call the factorial notation. So the questions here are, in how many ways can 2 people sit in 2 chairs? That's question 1. Question number 2, in how many ways can 3 people sit in 3 chairs? And question number 3, in how many ways can 4 people sit in 4 chairs? We're going to answer these 3 questions and look at the pattern and then generalize and say, what about if you have n people? In how many ways can n people sit in n chairs? That will give us what we call the factorial notation. So let's look at the first one then. 2 people in 2 chairs, right? Page 2, in how many ways can 2 people sit in 2 chairs? Well, our answer to number 1 will be as follows. Let the 2 people be A and B. Now there are 2 chairs, so the arrangement, the sitting arrangement would be the 2 people would sit as A, B, or they would sit as BA. You can clearly see here that we have exactly 2 ways. 2 ways in which the 2 people can sit in 2 chairs. Either when you're starting from left, either you start with A and then person number 2, which is B, or start with person number 2, which is B, and end with the first one according to the arrangement AB. So it's either A, B, or BA. 2 ways. Let's look at number 2. Number 2 basically says, in how many ways can 3 people sit in 3 chairs? So we're going to say again, let the 3 people be A, B, and C. In how many ways can they sit in 3 chairs? Well, we can have A, B, C, or we can have A, C, B, or we can have B, A, C, or we can have B, C, A, or we can have C, A, B, or we can have C, B, A. Clearly, this kind of arrangement shows you that we have actually 6 ways. They can sit in 6 ways according to those arrangements shown there by just simple listing. Let's answer the third one. Number 3, in how many ways can 4 people sit in 4 chairs? Well, now there's a bit of more work now to do. So we're going to say again, let the 4 people be A, B, C, and D. If we perform the same kind of arrangements of letters. We have, remember, these letters represent people. So we have A, B, C, D, or A, B, D, C. I'm changing the last two letters there. Or you can, so I started with A, B, and then C, D, A, B, D, C. Then I'm going to say A, C, B, D, A, C, D, B, and so on. So we're going to also have A, C, B, D, A, C, D, B. And then with starting with A, we end up with A, C, A, D, B, C, or A, D, C, B. Right, that's starting with A. What about starting with B? So we're going to have B, A, C, D, B, A, D, C, or we can say B, C, A, D, B, C, D, A, or we can say B, D, B, D, A, C, or B, D, C, A. What about starting with C? We can say C, A, B, D, C, A, D, B. We can also say C, B, A, D, C, B, D, A. Or we can say C, D, A, B, C, D, B, A. What about starting with D? We can also say D, A, B, C, D, A, C, B. We can also say D, B, A, C, D, B, C, A, and we end up with D, C, A, B, D, C, B, A. Clearly from here you can see that we have 24 ways in which 4 people can sit in 4 chairs. So let's look at what is really happening here. The observation, I told you we're going to look at the observation, that we're going to understand what's going on and generalize. What is happening actually here is that you have the following scenario. You have 2 seats here in the first one, and there are 2 people to sit in the 2 seats. So starting from left, the number of ways in which you can fill the first seat is exactly, if you like, 3 ways, 2 ways actually. Number of ways in which you can fill the first seat is going to be 2 ways. You say, in which are these 2 ways? Where either you can put in an A here or a B, so there will be 2 ways of filling that space. Once one person sits in that chair, there will be 1 person left. That person must go in here, and therefore by using the fundamental counting principle, basically says you must multiply the 2. We're going to have 2 times 1, which gives us 2 ways. Right. Let's look at the second case here. The second case, we have 3 chairs, 3 people. What is happening is we have 3 chairs. Now we have 3 boxes representing chairs, and 3 people to be seated in these 3 chairs, starting from left or starting from right, whichever direction you choose. I'm choosing starting from left. There are 3 ways in which I can fill that, chair. In other words, in which people can sit in that chair. It will either be person A or B or C. Once 1 person sits, there will be 2 people left. Those 2 people, any one of the 2 can go into that space. So there will be 2 ways of filling that space there. And once the 2 people are seated, there will be 1 person left. That one must go in the last seat. By using the fundamental counting principle, which basically says you must multiply these 3 numbers, we're going to have 3 times 2 times 1, and this gives us 6 ways. As you can see here, it gives us 6 ways. And yes, for the last one, if I may have this space here for the last one, let's say now we have 4 chairs. I'm going to have 4 boxes representing 4 chairs. So that's 1, 2, 3, 4. How many people do we have? 4 people, A, B, C, D. Any one of them can sit in that chair. Once 1 person is seated, there will be 3 people left. Any one of the 3 can sit here. Once the 2 people are seated, there will be 2 out of 4 left. Any one of the 2 can sit in here. Once 1, 2, 3 people are seated, there will be 1 person left. that one must go into the last chair. So now if you do perform the fundamental counting principle, which basically says you must multiply these numbers out, you're going to have 4 times 3 times 2 times 1, which exactly gives you 24 ways. Right, now you can see the pattern now. 2 times 1, 3 times 2 times 1, 4 times 3 times 2 times 1. Clearly it tells us that if there are 5 chairs and you have 5 people, the number of ways of sitting the 5 people in 5 chairs will be 5 times 4 times 3 times 2 times 1. So now we can perform the generalization and say, therefore, if there are n people, in general, therefore, in general, if there are n people, not 4, if there are n people, if there are n people, in general, if there are n people and n chairs, the number of ways in which the n people can sit is given by in which the n people can sit. I'm going to come and fix that one. Is given by n times n minus 1 times n minus 2 times 1, 2, 3 times 2 times 1. You notice this is coming from here. If the first number is 4, the second number will be 4 less 1. And then the third one will be that number less 1, and so on. So the numbers are decreasing by 1 as you go further to the right. So this is what we call factorial notation. So I'm going to say this expression here, this is what is known as n factorial, written as n exclamation mark. So we can basically say n exclamation mark is going to be n open brackets n minus 1 close open n minus 2. Remember there's multiplication all through here, so we're going to say times and then times 2 times 1. So this is your factorial notation. Now let me fix this one here, in which n people can sit will be that. Basically we are saying that the number of ways of arranging n distinct objects in n spaces is given by n factorial, and n factorial is n open brackets n minus 1 open brackets n minus 2 multiplying all the way up to times 2 times 1, and then you're done. Now this tells you that if you come back here and you say what is 2 factorial, the answer in your calculator, it will give you exactly 2. Let's check it. Here is the calculator. 2 exclamation mark, the answer is 2. The next number here, what is 3 factorial? The answer is going to be 6. Let's check if this is true. 3 exclamation mark, 6. The last one, what is 4 factorial? 4 exclamation mark, 4 factorial. You'll notice the answer is 24. So that is the story of factorial notation. Now, I want us to look at properties of the factorial notation. Properties of the factorial notation. The next item I want us to look at is properties of the factorial notation. Now, there's something special. Let's look at starting with 4 factorial. We said 4 factorial is 24. We can write this as 4 times 3 times 2 times 1, which actually gives us 24. But notice something, that you can also write this as 4 times 3 factorial, because from here to there, that's 3 factorial. So you can also write this one as 4 times, you can also write it as 4 times 3 times 2 factorial. Yes, 4 times 3 times 2 factorial, because 2 factorial 2 times 1. What about 5 factorial? Yes, you can write this one as 5 times 4 factorial, which can also give us 5 times, obviously you know that this is 5 times. If you want to carry on with this one, you would say, what if we just carry on and say 5 times 3 times 2 times 1, of course. But this can also be written as 5 times 4 factorial. And you can also write as 5 times 4 times 3 factorial, and all the way up to 5 times 4 times 3 times 2 factorial. So now let's look at something else. What if I am given what if I'm given 7 factorial? We're still looking at properties of the factorial notation. What about 7 factorial over 5 factorial? How do we simplify this? Well, we simplify this as follows. We notice something, that down here we have 5 factorial, so we can write 7 factorial as 7 times 6 times 5 factorial, and then all over 5 factorial. And clearly these two can cancel. So 7 times 6, the answer will be 42. Right? Please take note of that. What would be the next property that I want us to look at? So we have now so far looked at 1, 2. That's the third one. I also want to look at property number 4. There are many more properties, but I'm just focusing on what is necessary for what we want to do, which is prove the power rule. Right. What about if I'm given n factorial and I'm told I must simplify this? N factorial divided by n minus 1 factorial, like so. Well, this, the numerator, remember, you can write it as n times n minus 1 factorial all over n minus 1 factorial. If you follow what's going on here, I can write this as 7 times 6 times 5 factorial because of that 5 down there. So with this one here, if I may draw you back to the factorial, the symbol for factorial notation, here it is. I can cut it off here and put factorial notation there. It will be n factorial equals n open brackets n minus 1 factorial. Or if I want, I can continue up to here and I put factorial, or I can put n minus 3 factorial and continue, as you will see in the next few cases I want to look at. So here, these two cancel and our answer is n. What about if I'm given n factorial all over n minus 1, let's say minus 2 factorial? You would simplify this. Because of minus 2, I would have to say n minus 1 and then n minus 2, stop there, put factorial there, all over n minus 2, and I say factorial. Notice these cancel. My final answer is n open brackets n minus 1. Well, if you also want to continue and say, what about n factorial all over n minus 3 factorial? Well, this will be n minus 1, n minus 2, n minus 3 factorial all over n minus 3 factorial. You can clearly see that these cancel. So what is my final step solution? It will be n open brackets n minus 1 open brackets n minus 2, and that will be the final answer for this one. Right, I also want to look at two special cases. The two special cases are, what about what is 1 factorial? Because we've looked at 2 factorial, we know 2 factorial is 2 times 2, 2 times 1, which is 2. I'm saying 2 factorial is 2 times 1, and we know this is 2. What about 1 factorial? How about 0 factorial? So I want to look at this one here. And I want to say to you that this is actually equal to 1. And yes, 0 factorial is also equal to 1. And I want to prove these two in my next on my next page here, page 5. So how do we prove that 1 factorial is equal to 1? The proof is as follows. We know that n factorial is equal to n minus 1 factorial, or you can say n minus 1, n minus 2, and so on. I want to stop on that one there. We also know that 2 factorial, the answer is 2. 2 times 1 is 2. So if I let n be equal to 2 in here, I'm going to have 2 factorial will be equal to 2 open brackets, 2 minus 1 factorial. And what is this? 2 factorial is 2 equals 2 times 1 factorial. If I divide both sides by 2, I'm going to have 2 over 2 is equal to 2 times 1 factorial all over 2. These cancel. We know the answer on the left is going to be 1. These 2's cancel. What am I ending up with? I'm ending up with 1 equals 1 factorial. That proves us, gives us the proof for 1 factorial equals 1. So this actually implies that 1 factorial is actually equal to 1. That's the end of the proof for the first one. Let's call this number 1. Those are special cases. Number 2, 0 factorial. How do I prove that this is equal to 1? Well, the proof is simple. We know, again, that n factorial is n open brackets n minus 1 factorial. And we also know that what? We know from here that 1 factorial is actually equal to 1. Now here I'm going to let n be equal to 1. Because remember, n is a natural number. If you put 1 here, we're going to say, therefore, 1 factorial on the left is going to be equal to 1 times 1 minus 1. Put 1 here and there, there and there, and obviously factorial here. 1 factorial we know is 1, so that's 1, equals 1 times, what is this? 0 factorial. Divide both sides by 1, you're going to get 0 factorial is actually equal to 1, because 1 divided by 1 is 1. So that's the proof for that one there. Right, as far as the power rule is concerned, what we've covered so far in the factorial notation is sufficient for us to be able to understand the binomial theorem, and then we'll look at the power rule as a third video from this one. All right, if you're new to this channel, please subscribe, share these videos, and we request that you grant us the support by subscribing and sharing these videos, liking them. It will give us the impetus, like I always say, and the momentum to be able to generate more videos. All right, see you next time.